Hi guys. Today there is Codeforces around 7:27. As you can see in the bottom left, it is approximately 6 a.m. right now, so I have no doubt that's going to affect my performance, but I'm going to try anyway, and I guess we'll see how it goes, as always. I finally updated the sub count, so now I can remove this from my reminders. Okay, so they start from x minutes, 2x, 3x, t plus x. Sum of satisfaction of all participants. That's fun. They do have multi-tests, which is nice. LT. So let's see. Let's look first at the first participant and see how much they lose, or see what their dissatisfaction is, I guess. Does it include themselves? No participants have started the contest but haven't yet finished it. So it's everyone ahead of them. Does team matter? It should, right? Yeah, it should. Okay, this is fun. Okay, so it's going to be constant until it isn't, and then it's going to decrease until 0. So I guess, like, we look first at T. Where's my pen? Oh, come on, I just had it. Okay, yes. So we have like 0, and then 2, and then 4, and then 6, right? So for example, this will be this many. So it's t over x plus 1. So t over x plus 1 is the initial value. This includes themselves, that's fine, we can subtract that at the end. Essentially, like, here how many points over for it, then here how many points over for it, and etc. But it's also like haven't yet finished it, right? Oh wait, maybe it's easier. Let's just count first the number of people who started the contest and then subtract out the number of people who finished it. So the number of people who finished it, why is this so annoying? 2 times 10 to the 9th, huh? So the number of people who finished it will be 0, and then 1, and then 2, and then dot 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 up to n minus 1. So that's something we can count. It's n choose 2, or n times n minus 1 over 2. Just like a formula. And then the other part is like more annoying. So initially it'll be t over x plus 1, then t over x plus 2, then it goes up until n, right? So when is it n? It's n when you have t over x plus k, or rather t plus kx over x is greater than or equal to n. Which is to say kx is greater than or equal to nx minus t, or k is greater than or equal to nx minus t over x. K is the ceiling, right? Wait, now I'm confused. Yeah, it's the largest, it's the smallest integer larger. Okay, so if it has to cap at n eventually, right? Like the last person will end after they finish. So it should be n times x minus t plus x minus 1 over x. This is ceiling. So initially k equals 1, then k equals 2, etc. So it's t over x. I have to subtract that from just stop minus that. And it's plus equals n times m minus stop. That's like the leftover. Because we have like, even after this, then we get some like n left over until we get to the end. And then we have to subtract out this part, which is the number of people who have already finished, which is n times m minus 1 over 2, but because we also subtract ourselves, we might as well like have this be a plus, because now it's 1, 2, dot, 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 n. Alright, great start. Jesus. And it's all negative. Stop. Now we can debug this, because lovely. I was actually kind of right. So what happened here? Like, why is this so annoying? So this is 2. So I times 7. Okay, times 7 is right. So what happens here? At times 7. Two zero. What is t over x? Essentially, like, I'm taking the sum from 1 to n and then subtracting the sum from 1 to t over x so that we're left with only this. So why is that not doing anything? 202. That is 2. Stop is also 2. Oh, this should be n. That's why. Okay, that makes sense. Good. Okay, looks like it doesn't overflow, even with the worst possible answer. So I guess it's fine. Yeah. Fun problem. Could even get this wrong. I could see that happening, but whatever. I don't really care. Nice, okay. So what's with that then? What if we have like this, but worse? So in that case, everyone sees 2 people. What if we have like this, which is technically not allowed, but it should be like close to 0. Maybe 1 or 0? Wait, why am I doing this even? Actually, we only need to do this. We don't need to compute stop. Actually, this will be like n times t over x, right? Okay, that's interesting. Maybe we don't need this. I should get the same answers. But it doesn't. We still need this. What's the difference here? Is there a difference? So it will always hit n. How would it not always hit n? Because we can always count our cells. Can it overflow? I mean, it's 2e9 squared at worst. It's at worst, yeah, 2e9 squared. Is this equivalent? I don't understand what's wrong. Will this also be wrong? Still. Is there some like 111? Okay, so it'll be 0. 2, 2, 1, 1. Answer should be 1. Actually, this would be simpler to just get rid of this, but I don't understand. So if t is 4, it doesn't matter. T is 6, it does matter, right? Go bar 4 to 6. No. In this case, the first participant would see another person. GSN is also n squared. And the integer limit can handle that. Very, very confused now. So this will still work. What? I'm gonna give up on this, man. This is enough suffering from that. Subsegment, substring, PT letter k times. So you square the occurrence? No, what? K is the index of the alphabet. Okay. Okay, that's much easier. Why didn't we use... What happened with A? What is this? Okay, no multitests. Plus count, SI. I don't even need this. 26 J++. So it's prefix. RJ. If L is greater than 0, C minus equals prefix L minus 1, J. Res plus equals C times J plus 1. Okay, so this is, if I understand it right, which I hope I do, should be very standard. Yep, it's just using prefix sums to count the occurrences of every character. 5415, 4711. Yep. Okay, it's at most 100,000. I made too big an array, but it doesn't matter, I'm pretty sure. What is going on with A though? No two neighboring elements differ by more than x. Now from the sorted array. Okay, so we first create the initial groups, then we can merge two groups if we can put people in that sort of, okay, this is also much easier. I really don't understand what is with A. Okay. Sort. So essentially we're going to figure out for each adjacent person, like, how many people we need to insert to, like, have them be in the same group. BI is equal to, how does this work? So it's, AI plus 1 minus AI, and then it should be less than or equal to x, which means we also have to subtract 1 to sort of like offset it over x. Sort b plus n minus 1. If bi is less than or equal to k. Then we take this many elements, we do that. We can take them in like greedy order. And for the people that can already be in the same group, then that doesn't matter that much because it's already sort of handled. Is this printing n minus that? Yeah, to print n minus ants. Okay, yeah, we're just greedying it. How's n equals 1 actually? 1, 1, 1, 1. Good, okay. And of course, if some student is like useless, then we just do whatever we want with them. Like we can put them in the same group as someone else. What? Okay. What did I mess up here then? Um, 2, 1, 3, 1, 7. This is the number of merges we can make. X cannot be 0. Oh, wait. Oh. Okay, that would actually be a problem. If I had, for example, 511. This could be -1, and that could actually be a problem. So 511, for example, and I had like 11114. Yeah, but that should not be true. So in the case where this becomes negative, then 5111114. Yeah, the answer should be 2 here. I think that will fix it. I think that's the only edge case actually. I can make sure though. Yeah, that would allow us to get a higher answer than we would expect. Okay, gets past pretest 3. That's good. It's a lot of pretests. I guess they stopped having multi-tests here. How are people doing? Assume they have A, B, and C. This is stupid. I still don't understand what's up with this. So we're counting the number of people who started the contest before this person, and we subtract the number of people who finished it. And because they finish in order, the number of people who finished is 1, and then 2, and then 3, and then so on. The people who start the contest right? So the first participant will see t over x plus 1 people explored. The second will see t over x plus 2 because they see exactly 1 more because it jumps by x. The third will see t over x plus 3 up to n. It's something like 200,000. 2 million, and then k equal or x equals 3, and then t equals 2, for example. So then each person will see nobody. Then 1, 2 million, 3, 3, 6. And then this continues. Don't need this. N times t over x minus gs t over x, right? So t over x is 0, then each person will see nobody, because everyone will finish the contest before them. T over x is 1, and the people that will be seen are, for example, 2, and then 3, and then 4, up to n. So each person except Alaska will see 1. We're using long. We're using long here. V times v plus 1 over 2. I really don't understand. Product I. If you buy BI products, out of all future products, there's a 50% discount. What? Why would you need to buy more items per product? You might as well spend money towards the discount if you want. Assume some sort of exchange arguments. I want to finish N though. Or A, I mean. What if it's something huge? Like 1, 1, 1. Oh. That settles it. Right. Okay, right. Someone cannot see more than N people. Okay. Yep, that makes sense. Alright, that was done. Now we can solve actual problems. One item of product 3, one item of product 1. Right, okay. So we want as many discounted items as possible. So is it optimal to process in decreasing order of value? Is it ever optimal? Is it? What if it isn't though? It might also not be. In fact, I can very much see it not being that. So we buy from some item, let's say the most expensive one, maybe, until we can meet the first requirement. When some requirement is met, we instantly buy everything from that item immediately. If we start off buying from, say, the most expensive item, and then when we have finished the most expensive item, then, or not the most expensive, like the hardest item to get. Then what do we do? Now, would that be correct? In particular, would it ever be okay would it ever be better to buy from some item that's not the hardest to get? Like, if we do that, then we get some amount of discount items from that. But if we buy instead from the one that's hardest to get, then the item we buy will remain not discounted. We will, by default, gain a discounted item from that, right? We will, by default, gain a discounted item from that. Don't we? Yeah, so like I think we can, like, if we have an optimal strategy where we buy an item from like something that's not the hardest to get, then we can swap the buy into the hardest to get, and then we would still, like, the answer would either be the same or be better. Something would be discounted earlier, or it would be, yeah, I believe so. The item would have an easier time being discounted. Or would it? Would it? If it's there. If we have like some item over here that's hard to get, and then like some easier item, I'm showing that if we move this into here instead, then this would be better. And the reasoning is that this isn't always true though. Like, maybe this can't be discounted. Maybe this can't be discounted, but this can, for example. But like, how would that be discountable? It's strictly harder. How would that be discountable, but this can't be? We'll get the discount for this earlier. So we'd rather have this not be wasted on this. We'd rather have it be wasted on this. I don't know. I don't have a proof. It's not a good proof, but like, it's, you know, it's faith. I'm gonna trust it. So Cn to n for so I'm sorting by the requirement. Sort p plus n, reverse p plus n. L equals 0, R equals n minus 1, cur is equal to 0. So essentially we're doing 2 pointers. And we're either going to buy from the beginning or from the end, and so we're sorting in decreasing order of requirement, and then from the end, if we have enough, we'll buy at the discount. Save. And then we'll subtract the amount we save plus equals pi.f. No, pi.s frequency. Yeah. So while L is less than or equal to R, the requirement is the maximum of 0 and PR dot first. No, Yes, PR.first, the requirement for that item minus the amount we currently have, which could potentially be 0. Okay, so if rec is greater than 0, then we buy the minimum of rec and the amount we can buy from the hardest item, PL dot second. PL dot second minus equals B. Cur plus equals B. Else, we can buy everything from here. So save plus equals PR dot second. Cur plus equals PR dot second. So this is buying all from the cheapest item. And then PR dot second is equal to 0. If PL dot second is equal to 0, plus plus L. Minus R. Right, okay. Now C out 2 times total minus save. That should be it. The total price times 2 minus the amount we can save. Multi-tests. Alright, so we save 8. We save 3 here. Okay, so this all makes sense. Reading the pairs backwards, sort by the requirement in reverse order. Total plus equals pi dot s. Now, this is saying, what's the amount we would need to buy to be able to save on the cheapest item, or the easiest to get item. So if we need to buy some stuff, then we buy from the hardest item, and we buy the amount that we can get, either the requirement or the amount of the item that we need to buy, whichever runs out first. PL to S minus equals that, cur plus equals that, nothing else changes. If this is 0, then move on. Otherwise, we add that to the amount we save, add that to current as well. Okay. I've gotten enough wrong answers that like a few more penalties can't hurt me. But I mean, I think it's right to do that. Like I believe in the strategy. Passes a hidden pretest. Okay. That's good. So it is getting somewhere. That could also mean it fails system tests, which could like be a thing. I hope not. Hopefully like 1, 50, 20. 1, 50, 100. 1, 50, 50. 1, 50, 0. 50, 37. Okay. Sure. There are more solves on, okay, E and F are sort of equal. The Alice's computer is broken, so she can't play her favorite card game now. English is nice. Initially, he holds 1 card with 0 in the left hand and 1 in the right hand. In the 9th question, replace a number. Number Ki. After this action, you realize the numbers on the left and right cards to belong to given segments. Segments for left and right cards can be different. Formally, let the number on the left card be X. Okay. Remember, there was some other thing in the past where, like this, we sort of looked at it backwards and then we figured it out. So suppose we do look at it backwards, then how would this work? Or rather, we do something with this. Also, it initially has 1. Why does it have 1 in the right? Is that just like random? Okay, right. So our current state is, one of them is the previous card, the other one is some other card. There are a linear amount of states, and the linear amount of new states. Problem is, many of these states don't work. What is M? Why do they have M? I don't know why they have M. So this will work except for the fact that it's n squared, or yeah, n squared, so we can't really do that. So let's see. Nice query problem is surface card left hand. Okay, sure. And what's F? There's an array of integers. Thinks all the numbers in the arrays are strange. Choose a subsegment. Sort its elements in increasing order. Finds the center of a segment. Okay. Center of a segment. L plus R plus 1 over 2. Right, okay. So that's the right at the middle. The maximum distance. Okay, that's kind of interesting. So maybe we consider all elements in order. Consider all elements in order. Now, elements that are less than or equal to this value, are they all distinct? Does it guarantee that they're distinct? No, it does not. Equal elements can be arbitrary. Wait, what? So in this case, this can be so the 6's can decide to be on the right. So how do we factor in the number of elements? So essentially for odd counts, it's it really looks like an even and odd segment. Are you serious? That's annoying. Maybe we don't. Maybe there's some floor value here. In the first case, so we make a segment tree where everything is essentially 1 or 0. 1 or negative. So for the current element, elements that are smaller than this value will become we consider both. First we consider elements smaller than this value to be negative 1, and otherwise we consider elements larger than this value to be smaller than this value to be 1. We try both. We try both and see what happens. So for the odd case, so we get something like suppose balance is x. Right, so what's that mean? It means that so, for example, if we have, let's say n equals 5. If we're here, then the balance will be, if we're here, then we'll be greater than 4 elements. Counting our cells is weird. Why do they have to make them non-distinct? Okay, if we're greater than 5 elements, then the balance here is 5. Here the balance would be 3. We're greater than 4, less than 1. Here would be 1, here would be negative 1, here would be negative 3. If we assume x is less than 0, then we get something like, we can treat these separately. But if we count ourselves as bad, then now this is like negative 5, this is negative 3, this is negative 1, this is 1, and this is 3. So the position we're interested in is here. It's floor of n over 2. What about even? And probably one of the best ways to do indexing is just to work out some examples. X greater than 0, x less than 0. If it's equal, we don't care. Right, so here we have, this will be 6, this will be 4, this will be 2, this will be 0, this will be negative 2, this will be negative 4, this will be negative 6, this will be negative 4, this will be negative 2, this will be 0, this will be 2, this will be 4. So we're looking for the maximum absolute difference. And we take floor of that minus 1 over 2. So we find the largest absolute value we could ever get, and then we get floor of v minus 1 over 2. And I think that should handle everything. That will handle even the even case. Actually, no, it's different for greater than 0 and less than 0. Here, this should be floor of v minus 1 over 2. Because in this case, this is only 2 away. But in this case, it should be floor of v over 2. Because in this case, it's this many away. In this case, it's 3 away, which is better. Okay. So this then becomes not hard. So Cn to n. And we create 2 global segment trees. Essentially, we're going to query the smallest sum subarray that occurs here. And the way to do that is to say, we're at index here. We want the smallest stuff we can take on the left and the right. So we create like a segment tree that represents like each index is the prefix sum from here to the left, for example, like this, and then we can make a min segment tree over these prefix sums. And then we query the minimum prefix sum to the left and then the minimum to the right, and then that gives us exactly what we want. And as it turns out, the entire array is overcounted, right? I don't know, it doesn't matter that much. No, actually, yeah, the entire array is overcounted. ILV, tote minus equals v, AI is equal to v, then tote plus equals v. Tote minus equals AI, actually. So this is just set AI to v. All right, now for I equals 0. No, it should be like B. Then put I -1. Initially everything is -1. Now for equals 0, as then n, I plus plus. And then now for each value, for LLX at I, put I x1. And then now we do the same thing. So we need a min segment tree and a max segment tree. Jesus. So we need 4 segment trees. And we have a time limit of 2 seconds, which I guess is fine. So I need like both of the t's. So seg tree, max t, mxt, mxl, mxr, and then seg tree min t, mnl, mnr. Alright, so initially, mxl.init and c, mxr, and then we do the mins the same. So now when we update this, let's see. Actually, let's start with this. The difference is equal to bi minus v. How much does this element change? Then to plus equals d. And we can do the updating here. So mxl.update So because the segment tree represents a prefix sum, updating here for the prefix sums that represent like going left will mean that it updates all of these elements. So if this becomes plus b, then all these prefix sums get plus b. So it should be 0 to I. I forgot on my own signature works, right? Yeah, 0 I d, max r, dot update I m minus 1 d, and then min and max are the same. So min l, min r. Okay, now query l I query min and query max, I guess. Max. So we query the minimum prefix sum to the left. Min L dot query 0I okay. Min dot query 0I dot val v plus equals min r dot query I m minus 1 dot val turn v minus total max L max r. So for lx at I, v equals query min abs negative query min x. So it should be v over 2. So cx is equal to max cx v over 2. And this is query max. And this should be v minus 1. Okay. No return statement. Oh. That doesn't need one, that's why. Void. And we can do that, that's fine. 11001. Interesting. Is it always off by 1? No, it's not. Okay, yeah, it was worth a shot. Why is that true? Calculates the distance between its current position and the center of the subsegment. So we can always achieve 1, for example, or we can almost always achieve 1. What happens here? So C out X, V, and L. I'll put that here too. Right, so how does this work? By the way, we subtract tote because like of how it's counted. Everything is counted, over counted a bit. So minimum 4, negative 1. Max. Right. Wait, why? Everything's negative 1. It should all be small. See out min L dot query 0 0 dot val. It should be 5. Yeah, 5. Wait, no. V minus, okay. Right, it's the new value minus the old value, of course. Now it works as intended. Let's check the other one. Two, three, 1, 3, 2, 3, 1. Okay, good. Let's see. So all this makes sense. All this makes sense. It's like very simple code. The only part that would be doubtful is this, but I worked it out by hand. So I think it makes sense. 2, 3, 1, 3, 2, 3, 1. Let's make sure it just like doesn't have debug prints. Yep. I trust it. See how that goes. Pretest 7. Pretest 10. Could have time issues, I guess. How'd that go? Pretest 13, pretest 14, pretest 15. It's a lot of pretests. Okay. It is advancing through. So that basically leaves E. Unless this has some time issues that I need to fix. That's a lot of pretests. I guess that makes sense. It's kind of a bulky problem. So how do we do with this one? Well, if we did the n squared dp, obviously that wouldn't pass because it's n squared. So some states are of course not reachable, but if every state is reachable, then we have problems. Maybe somehow we think about it in reverse. Okay, 9:35. For 2 seconds, that's fine. How's this going? How are we doing now? Okay, despite horrible penalty everywhere else, this actually wasn't that bad. We're in the top 20, which is pretty cool. Yeah, pretty much the worst out of people who solved A, B, C, D, F. Jesus Christ. That is so bad. But, okay. Because I fixed A, like, after. Yeah, B and C were easy. Or, yeah. A was not bad. Wow, Tourist is doing this round. Cool. Maybe he's like screencasting or something. That's kind of interesting. And he started with F. By the way, I hope you can hear me. That'd be a good thing to check. I think like it's fine. I hope. I changed my mic angle a bit, so maybe you can also hear the keyboard. Okay, anyway, I'll leave that. So that's F, wasn't that bad. It's rather standard like the rest of the problems. And then what about E? How do we do E? Also wants the numbers on the left and right cards to belong to given segments. Formally, let the number on the left card be X and on the right card be Y, then after the I swap the following conditions. Yeah. So the problem is like when it's easy. If it's fixed, if we have to put this somewhere, then that's not that bad. What if we have like a better strategy? So the number of states could potentially be n squared. But like, is it? Yes. Yes, but is it? I mean, yeah, of course. But how much does it matter? Zero 0302 0402. Essentially, that has to be on the left. That has to be on the right. actually, the state will always be this card and then whatever card we had last time. So I want to see, like, if we put like card X down on the left, when's the next time we need to replace it? Put card X down on the left, when's the next time we need to replace it? So maybe it means we don't have n-squared states. What if we like what if we only care about states where the numbers are right next to each other? So we can pre-compute, for example, we're computing the intersection of the angles this way. That can be done with a segment tree. We can do interval stuff with a segment tree. We can do segment tree descent even. Nice if we didn't have to, but we could. 2.5 seconds. Does that mean it's supposed to be log squared? What's status on E? Do people take a long time? Like, Q. Theoretically, there is a log squared solution to this. 4 milliseconds. It's not the greatest. I don't really want to implement segment tree descent though. I don't want to implement segment tree descent. So I can just do the query. Soon it can be done, right? So look, for example, can we get to this state? Alright, so we can add in 2 fake queries to force us to have the 0 and 1, that's fine. What about like some other things? You can also test out, for example, 2 or 1 and then 5 something, and like 1 4 5 5 5 5 5, rather 2. starting from that's fine. We can add in 2 fake coordinates. So I assume we just put some card down here, for example, on the left. I'm interested in how far can we go on the right. So this will survive on the left for however long it wants, and then we also need to figure out how long can we survive on the right, like so. We figure that out for both of them. Make the minimum. And that lets us know this. Okay, this should work, I'm pretty sure. It's just kind of annoying in the way it works. Okay, so it's another symmetry problem. So A0 is equal to 0, OV0 is equal to 0, 0, OV1 is equal to 0, 0, A1 is equal to 1, LV1 is equal to 0, 0, RV1 is equal to 1, 1. This should be RV of 0. C and AI to LVI to RVI. Reducing for suppose we're going to put this down here, and that's going to be the end. this is only possible if we could reach this from some other state. Which is okay. Yes, it's only possible if we can reach this from some other state. Should we go over what I'm thinking here? Running out of space here. Actually, no, I'm not. So basically we consider like, when we put some stuff down like this. So we're considering what happens when this is the last card we put down on the left for a while. And we're just going to put stuff down on the right. Then we ask how long can we survive? So essentially we figure out from the left how long can we survive where this is the last card. And from the right, how long can we survive when these are the cards we're using? Then that will tell us which of these whatever states can we access. And then when we know we can access this state like this, now we can do the same thing, for example, for this state. We can assume now this is the last one we're going to use on the right for a while, and then push out to the left. And then the answer is possible. Yeah. Restoring the answer is a bit. Actually, I think it's fine. Yeah, I think it's fine. We just look at the parent state. Could be, actually it would be better to V2, and then that way we can do things like this. Maybe like this. V0, 1, 0, 1. That makes this easier. So now from here we just figure stuff out. Okay, this is just a pain to implement. I don't want to do this, but I guess we have to. So, set par. Like, implementing the beginning parts are kind of annoying too. Constructing isn't that bad. I need to remember that M exists, even though it's useless. I don't know why they have that, but now essentially mem set par -1 size of par. So push 0 0 push 1 1 for I equals 2 as an n equals plus. If par I 0 is not equal to -1, push I 0. Alright, should we check first the can set? Del for LX del IJ. That means it stops working at this position. Then can J dot erase I. No. X. So if can J dot size is greater than 0, then par IJ is equal to the any element from this set. This is the possible candidates for parents, and then push IJ. Construct. Well, t is equal to -1. If par m minus 1 0 is not equal to -1, t is equal to 0. If par m minus 1 1 is not equal to -1, t equals 1. If t is equal to -1, okay. Construct. So now we implement push. Right. So from push, we figure out the survival time. Then with the survival time, actually this isn't that bad. We figure out the survival time. Survival time requires some sort of DP, I guess. this actually isn't that bad. So dpn0 is equal to dpn1 is equal to n. I equals n minus 1, I is equal to 0. So if this is valid, for j equals 0, less than 2, j plus plus. If this fits within this interval, if vi j dot f is less than or equal to ai, and ai, it's equal, right? Yeah. Is less than or equal to vi j dot s, then it works, so we can continue surviving. So dpij is equal to dpi plus 1j. Else dpij is equal to I. This is the place where we die if we start going from here. Okay, now that works. Live it. If, no, not if. So this is can I t dot insert I del d t dot push back I. That's essentially it, isn't it? Find the survival time. I say that this can live up until then. Or wait, it's sort of like the opposite. It should be the not. Can not t, and not t. Okay. Worst is equal to, so it should be dpi plus 1 and then not t, right? So this is how much we can live on the other side. dpi plus 1, not t. Find less. So seg tree max t 2. RT LT. So RT T dot find less. This would be AI. How long do we live with this? If LV is equal to -1, LV is equal to n. RV equals LT T dot find more AI. If RV is equal to -1, RV is equal to n. Return min WLV RV. So now I basically just implement this second tree, and it actually shouldn't be that bad, right? I have this already. Make sure we initialize the second tree right. For j j equals 0 is then 2, j plus plus. For I equals 0 is then n, I plus plus. Ci is equal to v I j dot first. This is lt. So lt j dot init nc. And this is rtj dot init nc. Okay. Void find less l. What is this? So this is starting from I. Yeah. And this is starting from I. Start LV. So it should be 0, 0, and minus 1. Start V. That should be Ella. Find less R. So let's see. Mid is equal to TL plus TR over 2. If there's stuff on the left, if S is less than or equal to mid, then we try left. Oh, V is equal to -1. V is equal to find less R, so it should be 2 times I plus 1, TL mid SV. Right there, like some more fixes in this. So it completely covers the left side. If S is less than or equal to L, then it completely covers the left side. So if tree 2 times I plus 1, actually also, if TL is equal to TR, return tree I is less than V, then return TL, otherwise -1. Dot val is less than V, return find less R, go down this way, else go right. Mid plus 1, TR, SV. Else. If S is less than or equal to mid, we try going left. By the second tree analysis, this doesn't happen at all. Now, if we find something here, and there's no reason to go right, if P is not equal to -1, return P. Otherwise, return else. Otherwise, go this way. Otherwise, it's completely on the right. So we just do this. And then the same thing, but for more. More, and then this is more. So this essentially is this, and then this. Is the only cases. Okay, let's just try this. This is enough for now. It should be dot val. TL. I hope I didn't make that mistake elsewhere. I don't think so. Return -1. Where? Oh, same issue here. Return -1. This should be TL. This should be dot val. And actually, this should all be find more. That's a good thing to look for. Yep, okay. No way it works first try, but that prints yes. Nice. Does it always print yes? What? This doesn't make sense. I go 0. See Okay, let's find out what's happening here. This should have a parent. That doesn't make sense. Also, let's print the same thing, but for DP. So how long do we last here? So 3, this DP should be, on the left side it should be N, that is correct. On the right side it should be, here it should be, we should die here. And then here we would die there, that's right. Okay. Let's see what's happening with push. So 0, 0 should live until 2. That's wrong. No, that's right. Oh, this is intentional. Okay. Par 0. Par 1, 1 is equal to 0. That I should just set manually. Well, actually, this doesn't matter anyway, but okay. Now, 1, 1 can live until 4. Is that the case now? Yes, it is. 2, 0. And we start at 2. 2, 0, restart at 2, and then go into a 4. Is correct, is it not? Two, 0, restart at 2. That is also, okay, that's also correct. So what's happening here then? So nothing lives until here, so why does this happen? Two. So 2, 1, 2. Oh. So it doesn't even last that turn. Right. Okay. Just copy this loop. No, this should be negative. Yes. It should still work. Yes. Okay, let's see now. Don't think I need DP anymore. DP seems fine. Okay, so vector LO res. LO par n minus 1 t. If I is equal to p, p is equal to par I t. Res dot push back t. Okay, let's see how this works. 0, 1. This gets now as expected. This will print something like 0, 0, 0, 1, 0. Is that okay? No, it's not. Why do we do that? What? How is the parent itself? Stop it. How is the parent itself? This is wrong, isn't it? So we can't put that there, because then we end up with something bad here. How is the parent itself? Something is messed up here. I think it's with del. I think this is a special case. This also means it's the smallest parent. Which means it shouldn't work. Okay, I don't understand how this happens though. So 5, okay, and then 4. And somehow this can live until 1. So 0, 0 can live until 3. Put this down here, then we put 1 down there, we put 3 down there, and we put, so that will die there, which makes sense. 1, 1 can live until 6. How does that work? So we put 1 down there. Wait, is the point to... Now I'm very confused. 3, 0, 3, 0, 2. What? One, 1, 6. So if we put the 1 in the place, and the 1 will survive for a while. Where does it die here? Actually, this is correct. Slightly. It's a bit wrong, but... So where's the problem? So this 4... can put that in 0. Then we can put that in 0, which is wrong. This has to be 1. Why is it not 1? What's being messed up here? I'm not going to debug in time, of course, but just what's being messed up here in general. I want to figure this sample out. Zero 3 0 3. So the parent of 4 should not be 1. Oh, this is messed up, that's why. Okay, yeah, it's because this is messed up. This should die at 4, and so we need to switch there. Keep check DP. This is right. Is it? So why is that not doing this then? Oh, right, okay. So we start here, this will survive till the end, which it will. So the problem then is here. TR, return this. So all I'm concerned about is 1 and 1. Why would you be 6? This is minimum, right? And LT is... Oh. Is that why? Is that really what this is? This entire thing is because of that typo? I hope that's not the only bug. I would be mad if that was. Can't submit anyway. Man. I really hope that's not the only bug. That would be so frustrating. I guess once system tests are over, which they probably never will be, I'll just submit this and then see. Oh my god. Do this entire thing in that one single bug. Right has to be min. Left has to be max. So, oh, that's not the only bug. Because I was like 2 minutes off of that. If it was 5 minutes more, I would have gotten it. Or wait, if it was 5 minutes more, I would have figured out that bug, and then we would have seen. Let's also see this, right? So this should fail. Okay, well, resolution. I guess I'll go over all the solutions then. Fairly sure my solution to E is correct. I just missed it by a bit, so I will go for that. How much would I have gotten if I had done? Oh, I wouldn't know anymore. I think it would be a fairly good place though to have both of these, to have E and F, right? I don't know. That's frustrating. I didn't even notice that. Okay. Well, in any case, let's do some stuff. Problem A, which gave me more trouble than any of A to D, says you have some contestants that are going to start. You have some contestants that are going to start competing at time 0, then time x. Or yeah, at time 0, then x, then 2x, then 3x, then dot dot dot. You have n contestants. And then each contestant is going to finish exactly t minutes after they start. So this will finish at t, this will be t plus x, this will be t plus 2x, this will be t plus 3x, etc. And so we want to figure out for each contestant, how many for example, for this contestant, how many contestants do they see where A, they've started the contest already at this moment in time, and B, they haven't already finished the contest. So if we represent these people as intervals, so it's like 0 to t, and then the next person is x to t plus x, and the next person is 2x to t plus 2x, and then the next person is 3x to t plus 3x, and then etc., right? I'll do the diagonal dots. Then we're interested in, for this person, for each person, how many intervals do they intersect? So for example, for this person, it would intersect these two. And suppose I actually drew out another interval, 4x, then t plus 4x. Actually, it's more like how many intervals, it's not how many intervals do they intersect, it's how many intervals does this point intersect. So like how many intervals of these, of the previous one, wait, but this doesn't make sense. No, it's how many intervals does this point intersect as a whole. Yeah, so for example, this guy would intersect with these two, but not these two because they've already finished the contest. Sorry, this problem is so trippy for me. So essentially the way this is going to work, essentially the way we can do this is we can split this up into like two parts. First, we count the number of left endpoints we have. And then we subtract out the number of intervals where their right endpoint is to the left of this one. So we're essentially interested in, for this person, how many people started before him? And then for each person, how many people ended before him? And then because everyone who ended before him will also start before him, that's fine. And we just subtract out the number of people who ended before and not after, because the people who ended before will not be counted because they won't intersect. So first, let's do the easier part. Let's count the number of people who ended before, and therefore they won't be counted. This is simply like the position of the person, because by default, this person finishes first. So in some implementations, this like counts itself, which we don't want to do. So in this case, we would have like one person finishing before this, and the person is themselves. And then here there's 2 people, and then here there's 3 people, and here 4, and here 5. It's just the order in which they finish, because everyone that finishes before them, and we know like the positions of everyone. So this part's simple. And then the other part is asking how many people are to the left. Well, the first person will have the floor of t over x plus 1 to the left. It's the number of x such that like that is less than t. So for example, it's the k. such that kx is less than or equal to t. And then we count k plus 1, because we also count 0. That's the number of contestants we'll see. And then the next person will see t over x plus 2. And then this will continue up until we get to a person which sees n. And then it will continue to be n, because we go farther to the right, so the number of people can't decrease, so it just stays n. Right. And so basically we have t over x plus 1, t over x plus 2, ... up to n, and then a bunch of n's up until the end. So the way we can think about this summation is essentially we break it into two parts, like the beginning part and then the ending part. So up until the first n, and then we count the last n separately. So how many elements do we have in this group? It's essentially every element on the closed interval from t over x to n, open interval. And then all the rest of these elements will be n, right? So we just need to count the number of elements on this and then subtract that from the total, and then that gives us the number of elements that are not n, or that gives us the number of elements that are n. So one way to think about, so we can just like break this into two parts. So the number of elements we have here, by a bit of math, it turns out to be n minus t over x. And then, sorry. Yes. And then therefore the number of elements here is actually just floor t over x. Right, and so this part we can represent as like the sum from I equals 1 to n of I minus the sum from I equals 1 to floor t over x I. So we basically just count the sum from 1 to n, except we exclude the part that we don't care about. So we just subtract that out. And this is nice because the sum from I equals 1 to k of I is equal to k times k plus 1 over 2. I will not verify this formula because it's very common. You can probably search it somewhere. Yeah, sorry, I'm too tired to go over details. But anyway, so this is one part. And then this is the other part. It's simply n times t over x. Except there's a way we can simplify this formula. And the reason is because this is also the sum from I equals 1 to n of I. So in the overall formula, we write like, so we do the sum of the left values. So it's the sum from I equals 1 to n of I minus the sum from I equals 1 to t over x of I plus this part. So plus n times floor t over x. And then minus the sum from I equals 1 to n of I. So as it turns out, these cancel out because they're the same. So we end up with just n times floor of t over x minus the sum from I equals 1 to t over x of I. And that's the final formula. There's one final detail, which is what cost me so many wrong answers, is that we can't, like this value could be huge, but at most we can see at only n people. So we need to cap this at n. And so the way we do that is we simply, we say like instead of t over x, we say some like modified value, which is really like the minimum of t over x and n, I'm pretty sure. It might be t over x plus 1. I don't actually remember. Actually, I'm not sure what that's right now, but okay. Yeah, it's the minimum of t over x and n. Right? Because otherwise, yeah. it kind of doesn't make sense actually. This should be m minus 1, but I think because the way the formula works, either is fine, I hope. Or I'll fail system tests and that will be a thing. But yeah, okay, that was A. It was annoying. Essentially, it comes down to that formula. I don't know, I mean, there's probably a better way to do it or think about it, but I don't have anything. Probably because it was early and I overcomplicated it. Okay, this one's much easier. Basically, it just asks us to count the frequency of each letter and then multiply it by its position in the alphabet. So for each A, we'll get 1 times that. For each B, we'll end up with 2 of those. For each C, we'll end up with 3 of those, etc. Up until Z, or we end up with 26. So essentially, we have a bunch of queries. We need to count the number of A's on a range and then multiply them by 1, and then count the number of B's and multiply them by 2. Oh, and by the way, I should go over my code for A, I guess. No, not this. This is just very simple. It just implements this formula. Take min n t over x, and then this is the sum. We just do that. Got B, got C. Cool. So for back to B, essentially we just keep prefix sums. So we keep a prefix sum of like f of I and C for the character C is how many of C do we have on the prefix from 0 to I, which is to say S from 0 to I. Then to answer how many of C we have on LR, well, if we want this range from L, I'm going to capitalize it. If we want this range from L to R, we can use the prefix sum from 1 to R, except we have some extra part that we need to get rid of. We want to get rid of this part. So we subtract out the prefix sum from 1 to L minus 1. So this is f of RC minus f of L minus 1C. If f of L minus 1 is like negative or goes off the string, then just have it return 0. We just exclude everything that's not part of it. So if nothing's not part of it, then just have it be 0. And basically we do this for each character, and then we can just, this just gives us the count. Then the answer is just the sum of each character times its frequency. So we do prefix sums here. Then here we, for each query, we read in 2 values. Then we say, yeah, so we keep the prefix sum, we query the prefix sums, then we use this formula. So it's the number on the right minus the number to the left. And then we add that frequency times the position of the character in the alphabet. You can reduce it to a number by subtracting out A, so that like A maps to 0, B maps to 1. You can do it to A maps to 1, B maps to 2, etc. if you like one index. Either way, you keep prefix sums for each character and then just like add stuff. I think I got C already. Yeah. Did I get D? No. Okay, C is like a thing. I think it's also like not that bad. All these are like very, very standard. Yeah, I'm sad about B. Okay, so C is asking we have some people. We're going to sort them. We have some parameter k, let's say k equals 5. And we have some people like 1. We have some people with like certain values or whatever. I don't have a creative enough mind to come up with a story. 34 and then like 100 or something. Or I don't know, 34. Right, so essentially what we're going to do is we're going to break these people into groups so that between every adjacent, wait, is that how that works? Yeah, between every 2 adjacent elements in each group, their values differ by at most k. So in this case, 16 minus 12 is less than or equal to 5, which is true. So if we break groups up like this, then this would be valid. And we can't do better, because like just try, you can't, right? So, and also these differences is 0, so it's fine. Essentially, we want to find the minimum number of groups we can split them into. But there's also like something else we can do. We can add elements in between. So actually, k is wrong. This should be like x, I'm pretty sure. Yeah. So x equals 5, and then we can add elements in between. So for example, I can add up to k elements. This is the actual value of k. So for example, say I can add 3 elements. And then in between these guys, I can add 21, I can add 26, and I can add 31. And then now it would be possible to break all these guys into the same group, which you can verify manually if you want. Or I can also add, for example, 6, and then 11, and then some other value like 17. And then now I can break these guys into groups. Or I would include the 17 here. Alright, or I could do something useless, like adding in 6 here, and then 21 here, and then 26 here. And then like it doesn't help, but it's the same idea. So by adding in students, what's the minimum number of groups you can make? So essentially the way this works is, the minimum number of groups is really like the number of pairs of people who can't be in the same group. So these two cannot be in the same group because they're too far apart. These guys can be. Actually, this is dumb. I'm gonna draw a line for impossible and a circle for possible, and you will have to stick with it. So these guys can't be in the same group because they're too far apart. Same with these guys. These guys are close enough. These guys are close enough. So to make 2 people in the same group, we need to insert elements so that they become close enough. So the best thing to do is, if we want 1 to be close to 12, first we insert 1 plus 5, which is 6. Then we insert 6 plus 5, which is 11. And then 11 is close enough, so this works. So how many elements do we need to insert? Well, it's the value such that... So let's take the difference. So 12 minus 1 is equal to 11. Then we need the value y such that x times y wait, no, that doesn't make sense. Or does it? Does it? No. Hang on. I'm trying to like figure out the way this works, right? So it's x times y plus x is less than or equal to, no, greater than or equal to 11, or the difference. So let's call this d. Right, so x times y plus 1 is going to equal to d. So solving for y, we get y is greater than or equal to d over x minus 1, which doesn't actually make sense. Maybe it does, because that means y is equal to the ceiling of d over x minus 1. I had a different formula. I think this it ends up being equivalent because like relationships between ceiling and floor. But it's like the floor of d minus 1 over x. Yeah, this makes sense. Okay. So this is the number of elements we need to insert to make this work. I think there's probably a better way to derive this. I just like didn't because I'm not being smart right now. But essentially that gives you the number of elements you need to insert. And then because like each pair of elements is independent, we can do greedy on this. So for example, here we need to insert 2 elements. Here we need to insert 0. Here we need to insert 3. Here we need to insert 0. And we want the maximum, so we can essentially just do greedy. Let's take the pair of elements that takes the minimum number of insertions to fix, and then fix that. And then take the next smallest pair and then fix that, and then so on, until either we can't anymore or we fixed anything. And the way to do that is we simply create the array of these, like the amount of things the amount of insertions it takes. We can sort that and then iterate through and then just like go until we run out of insertions. And also there's a special like thing that if d is 0 and x is 1, then this y could actually be -1 with this formula, and we don't want that, so it should become 0. So in this case, I max it out with 0. This was the case for this was the reason for my wrong answer initially. So it should be maximized with 0, and then this is the difference. Then we sort this array and then do some greedy. And then the answer is, this is the number of people we can have in the same group, so the minimum number of groups is n minus that. Okay, for D, I don't really have like a good proof for this, so I'm sorry that I'm not smart enough to prove things right now, but essentially for D, we have a bunch of items. Each item has some requirement for what you need to do with it. For each item, you need to buy some certain amount. So for example, so each item has x, y. You have to buy x. And when you have y items in total, over all items, so like when you bought y items total, not just y of this item, like y of any item, when you've made y purchases overall, then you get a discount. Specifically, you get a discount of like, normally you pay 2, but now you pay 1. So essentially, what's the minimum number of items? No, what's the minimum like cost it takes to buy all the items? And so the basic idea is you want to get as much discount as possible, of course. You want to maximize the number of items that you buy at a discount. So sort of like intuitively, you don't want to buy an element from the lowest unless it's discounted. Or like, I'm going to call like the cheapest item, like the one that has the lowest requirement. Because for some reason, like when I was explaining this, when I was doing this problem, I just kept using that word even though I don't mean to. So I'm just going to clarify that now, that the cheapest problem is the one that like has the lowest requirement. Right, so yeah, so what's the cheap? Right, so we only want to buy from the cheapest item when we can get it discounted, or maybe we can't get a discount at all, but we want to try to buy from it only when it's discounted. So what do we buy from to try and get that discount? Well, also intuitively, it makes sense to buy from the item that is the least likely to get a discount, because like the cheapest item is definitely likely to get a discount if we buy from a more expensive item, but the most expensive items are least likely to get a discount, so we might as well buy those at not a discount. There's probably some nice proof for this that I don't know at all. So essentially the idea is at some current stage, we buy from most expensive. We always buy from the most expensive. Unless we can buy at a discount. So if we don't have a discount, this is our strategy. Or we'll go like item by item. If we don't have a discount, we buy from the most expensive. Otherwise, if we have a discount at some item, like at the cheapest, buy that discount, of course, because there's no reason to not do that. So this is the strategy. It's sort of like intuitively makes sense. I really don't have a proof for it, so I'm sorry, I can't think of one. It's probably like reasonable, but then the solution just becomes simulating this strategy effectively. And so one way to do that is to do 2 pointers. So if we have a discount, then it's always going to be at the cheapest item. So what we can do is we can sort by the requirements. So for example, let's take this. So we have requirements of 2 2, 4, 7, 8, and 8. And then from those, we need to buy 1, 2, 2, 1, 2, for example. The order of these don't matter. So currently we have 0. So the first thing we would do is because we don't have any discount on here on the cheapest one, we buy from the most expensive. And the amount we buy is the smaller of whichever, like, however many we need to buy to get this, or the number of items of this we have in total. Whichever one is smaller, we buy that amount. So in this case, they're actually the same. So here we would buy 2, then this becomes 0, and now this item's done, so we move the pointer over to here. And now we have enough to get this at a discount, so now we buy this item, and then we get this much discounted. And then now we move the pointer over here. And then now the current amount is 3. Actually, I'm going to change this a bit. So suppose this value is 2 instead, because why not? So then here, the requirement is 1. So we only need to buy 1 from this. So we would only buy 1, and then this would become 4. And then now we can buy at this discount, so we buy 4. And then here we get 6. And then now we buy the other one here, so now we get 7. And then here we buy these at a discount, so we get 9, and then it finishes. And so overall, we just keep track of how much we got discounted overall, and then we subtract that from the answer. So it's very much like 2 pointers. We just decide what we need to do at each step. If there's some requirement, we buy the minimum of the requirement and the amount we have of the current item. And then otherwise, we like add to the amount that we get at a discount, and the answer is 2 times like the total number of items minus the amount we get at a discount, because we only pay 1 for those. Yeah, that's how that goes. Okay, E, which I think I was very close to, and in fact I have potentially working code that passes samples, but not today. That is not how it goes. So for E, I don't know, I don't really want to go over the statement, so I just won't. I think if you're at this point, you can probably read well enough, and if you don't understand, then like reread it. But yeah, essentially, so we consider the like basic DP solution. So we consider DP xy, where x is on left and y is on the right. And because having like the larger of these determines which card you're currently at, that means that we only have n squared states. And so this is doable, but of course it doesn't work because n is 10 to the 5th. So we need to do a bit better. And the idea is that we don't have to like consider all the states. Basically, we can get away with only considering dp of x and x minus 1, and also the other way around, dp of x minus 1 and x. So we're only considering the point, like, essentially our strategy is going to be like, we put some stuff on the first pile, and then we put some stuff on the second pile, and then we put some stuff on the third, or the first. And we go back to the first, and then back to the second, then maybe back to the first, and then back to the second. So we're considering only these change points. We're considering only the points where we change which pile we're putting stuff on. I guess this is also a change point. And so to help sort of this idea, we can put 2 fake like requirements here, where this is 0 and this is 1, so that it sort of requires us to have the initial starting cards. Wait. Oh, that's unclear. Okay. Wait. 1 card with number. Oh, okay. I thought this was like, this was value 1, which is actually sort of subtle. Yeah, I thought this was value 1. That is actually like rather subtle. Okay. I hope that doesn't change anything. In fact, let me just test that right now. Nope. Okay. Okay, that would have... Good. I wouldn't have noticed that before. So that means this code wasn't necessarily working, and that's fine. But okay, so how does this work? And we consider only these breakpoints. And so now we're asking, from this breakpoint, what other breakpoints can we get to? So actually this refines our state a little. The new and updated state is dp of so we consider like dp0 of I, or it means we just on pile 0, or like the left pile, we just put I down, and then it means this is the last thing we're putting on the left pile for some time. So now we're only going to put stuff down on the right pile. And then dp1 of I is the same idea. We just put I down on the right pile, and now we're going to start putting some stuff down the left pile. And then we'll change it up later, but now essentially this means that with this we can do better. With this, it's enough to get the answer, because like if dp0 of n of the last element, like n-1, and dp1 of n-1 is set, then that's fine. And otherwise, it's not. Right. So essentially now we just need to compute these states efficiently. And it basically asks like, is this possible? And if so, like store the parent so like we can recover the answer. But now we have linear states, which is good. Before we had quadratic states, which is not something we can optimize. So now we've reduced the number of states, and now the transitions are possibly O of n, but it turns out we can improve them to like log or something. So the question we ask is, for example, consider dp0 of I. So we have some cards here. We just put this down, and now we're going to put cards down here until we can't anymore. So what can we transition to? Well, basically we can transition to anything we can as long as this strategy works, right? So we need to ask two things. How long can we last on the left side, and how long can we last on the right side? And then this can transition to the minimum of those two. So first, how long can we last on the right side? This simply asks, if we say that we're only considering the right side, and we're putting every card down on the right, how long do we last? Well, this can be computed with essentially like dynamic programming. A separate dynamic programming, which is kind of dumb, but I don't know why F was considered harder than this. Maybe there's some easier solution, but I don't get it. So this is essentially dynamic programming. We're saying here we used this many values. No, what? Okay, let me actually think about what I'm saying. I don't know what the hell that was. Essentially, we compute this like other. Let's call this array like live. Live, for example, here we need live1 of I, or I plus 1. And it basically just asks like, how long do we last when we start here and then we put every card on the right, and then we're only considering the right constraints. Or like the constraints on the right pile. So either the transition is, for example, consider at this I. So either we lose here. So lose, then it's just I. So let's consider we're computing, I'm gonna use, I don't know, cyan for this, or not cyan, turquoise or whatever. So like, so for computing live one of I, if we lose here, then the answer is just I. It means we die at this position. Note that this is like exclusive, so this means like live I is the, actually it's the position where we die, or where we lose. And if we win, then it's however long we can last on the rest of it. So it's live one of I plus 1. It's however long we can last. We survive here, so now we're asking about this position. How long can we last here? And then as a base case, we can set the endpoints to like themselves. So like live 0 equals live 1 is equal to n. Right now, live 0 of n. Yeah. Because if we reach n, we win. If we reach n minus 1, we win, so that's fine. And then we compute the array like going backwards from the end so that these transitions work out. So that lets us handle the other side. Now what about the current side? How do we find out how long this card can last? Well, there are two cases for some interval not being satisfied by this value. Consider we have an interval x, we have a value x, and we're considering interval LR. Either we have x here, and then, I'm gonna capitalize again. Either we have x here, and then the entire interval is on the right side, or the entire interval is on the left side. So in the first case, the value of L is, x is smaller than the value of L, or in this case, x is larger than the value of R. So only one of these cases can be true, but if either of them are true, then it's bad, right? So we essentially need to find out if there's some L that x is smaller than, or if there's, if there's some L that x is smaller than, or if there's some R that x is larger than. In particular, what's the first L that x is smaller than, or what's the first R that x is larger than? And so we're essentially asking that. So this can be done using a variety of ways. For example, we can binary search on a segment tree that supports minimum query or and maximum query. We can also do segment tree descent, also something I'm not going to cover here, but essentially like, maybe I will. We do binary search within the segment tree. So for example, we're here. We ask, is the minimum value on this range small enough? And if so, we only consider this range, and then we just go into here. And here I'm assuming we're looking for an R that's smaller. So if the minimum value here is small enough, then we know the answer is within this half. So we can kill off this half and only search within here. And otherwise, if this is not small enough, then we have to kill off this half and then search within here. The problem is that it's not exactly perfect because we have some like starting value too. Like we're looking for greater than or equal to I, which isn't perfect. But as it turns out, by a similar analysis to the complexity of a segment tree itself, that if we check both halves and then we like break intelligently, then overall it'll still be log n total. And by break intelligently, I mean like use as much information as you can to prune out as much searching as you can. Yeah. So essentially, this tells us how long we can live overall. It's the minimum of this live DP recurrence and the segment tree descent queries. Or maybe there's some better way to do it, I don't know. But maybe like nearest greater value or something. I guess that would work. So that'd probably be easier. So maybe the whole thing can be done in linear time. No, maybe. Yes, actually, it can, but I'm not going to go over that. well, just like we can have a log, it's fine. The time limit's like 2.5 seconds. But I think this whole problem can be done in linear time, which is kind of cool. So then like here, this dp value essentially means that if we can reach x, then if this is true, then every dp1 from I plus 1 to x is true. And we can set all those parents to this. And so the way to maintain the parents is if we say dp0 of I works from I plus 1 to x, so then it fails for example, x plus 1. Then we can essentially we can keep like this global set of all the possible values that work. And then at this point, we insert into the set position I, and then here we remove I. And that way I will be in the set for exactly the time that it's alive. So that would work for constructing parents. Okay. I think that handles everything. I don't know. If there's something I missed, you can ask about it in comments. But essentially, yeah. And so here we create two fake things that sort of represent that we have to put zeros down in the beginning. And I thought this was a 1 for some reason because of the way the statement was worded. Like this looks like it has a value 1. And I was actually confused about the fact that they didn't have that in LaTeX, so maybe it was like my own fault, but whatever. I think like they could have not used the number. That would have been nice, but whatever. It didn't actually make a difference for me. So essentially we create two fake cards, we read in values, we compute this DP array. Either if this works, then we like inherit from the next value, otherwise we die here, so we have to use this. This is just initializing the segment trees. I think we can use like nearest greater element or something. It kind of works out. No, it doesn't. Wait, never mind. It doesn't because like it's not the same thing. But maybe it is? No. It's not perfect. Maybe we can't do it in linear time, but I mean, it's not that big a deal. So here we have can, which is like candidate. It represents like the candidates for each side. And then for each thing that we have to remove, we have to do that. Except it also gets like kind of weird with the way I implemented it, so I also have to do it here, but like don't worry too much about that. If you also have to do it there, that's fine. Like think about what your implementation does. Then we say if there's some candidate, then this is that candidate is the parent. And then like if it's I, this is also something to do with my implementation. You can probably implement it better so you don't have to have these edge cases, but and then this value push is essentially like we push if this is possible, then we sort of like figure out what we can reach from here and we set all of those to true. And so initially we also push like the initial two values, and then that sort of lets us handle that. And then it's just construction from there with the parents. That part, I just hit the mic. That part should be relatively simple. So yeah, that handles that. Okay, lower time on system test. Interesting. So where am I now? Like, wasn't that bad. Did Turris not solve E? They just like give up or something? Interesting. How's the room? Yeah. That's unfortunate. Could have done better, could have done better, could have done better. Could have gotten E. If only I didn't waste so much time in the beginning with A and whatever. Right, like how much time did I actually waste? Like this was 13 minutes in and 60 minutes in. It was just very bad. Oh, FSTs. That happened. TLE on... How do you TLE on this problem? Very interesting. Could have been weird. That's... runtime error. Interesting. And then this had wrong answer. This had, no, different tests. Cool. Was this an FST? Still in queue. Let's see. Yeah, I'm not happy about this. Should have done better. Should have AK'd. Would have given us a very good rank. But okay, last problem. I don't think I would have, because I wouldn't have noticed that nuance in the statement either. Last problem, I'm also not gonna go over the statement. So basically, the fact that we think about center sort of also makes us think about the median. And with the median, one common trick to do is like, if we're asking like, is x the median? Then we set values less than or equal to x to -1. And for greater than x, we set them to 1. And then to see if it's the median, we can like, we count the negative ones and we count the ones. So the negative ones are values less than or equal to x. Equality is sort of weird, but it'll work out. And then for the values less than x, or for the values greater than x, they add to 1. So then, actually, let's just assume there are no equal elements first. I'm just going to get rid of that part, because it doesn't matter that much, and we can handle it differently in this problem. So if it's less than x, it's -1. If it's greater than x, it's 1. So this is the median only if like we have an equal number of elements, right? So that x is near the center of this sorted array. So then the sum of this should be 0. Or if it's even length, then maybe it's 1 or -1. But the sum should be 0 or like close to it. Oh god. Oh. That kind of hurts. I don't know what hurts, but something. And so this sort of helps, this idea helps us also in finding the position in the sorted array. So let's just use this, for example. So consider n equals 5. Right? So what are the values for each position? If we're in this position, then we're greater than, actually I'm going to go back to equal to now. We're greater than or equal to 5 values. So this position is 5. Here we're greater than or equal to 3 values, so this position is 3. Here 1, here -1, here -3. So with this, if we take this value and then we floor it, this gives us the distance from the center. So in this case, the floored value is -2, -1, 0, 1, 2, which is of course what we expect. Yeah. And so if we consider even in the same way, then here we have 6, 4, 2, 0, -2, -4. So here, this corresponds to a distance of -2. No, this corresponds to a distance of -3, -2, -1, 0, 1, 2. So in this case, it would be enough to take the floor of v minus 1 over 2. And conveniently, that also works for here. So we can in fact do v minus 1 here as well, and then that works. So we can handle odd and even in the same way without having to do some annoying like parity casework, which is what I thought it was initially. So this handles what's the farthest to the right that x can be. And then for the farthest to the left, so to handle the farthest to the right, we want x to be as far as possible, right? And so every value equal to x, we also set to -1. So the x will be like greater than as many elements as possible. And so if we have multiple x, we would move this x to as far to the right as possible. And then what about when we want x to be on the left? How far to the left can x be? And now this is sort of where we handle the equality. In this case, we want x to be to the left of all of its equal elements. So this is strictly less than now, and then anything greater than or equal to x will be 1, so it'll be to the right of it. So anything greater than or equal is considered to be greater. So then you can do at the same indexing. It turns out here you only want v over 2, not v minus 1. So yeah. Then basically we just have to figure out for both like to the right and to the left, what's the smallest and what's the largest values what we end up with. Like, what's the smallest subarray that contains X and the largest subarray that contains X? So another way to think about this is consider the position of X here. We have to take this. We can possibly take some stuff on the right, and we can possibly take some stuff on the left, sort of like independently. So essentially, it's like, what's the minimum subarray sum we can get from here, and what's the minimum subarray sum we can get from here? So to answer this one, for example, this side, we can make a segment tree where each value corresponds to the prefix sum. So this is the sum from this to the prefix, this is the sum from this is the sum from this, etc. And then doing like a range minimum query over this will just give us the answer. And then we also need to subtract out this part because it's a prefix sum, so we only care about up to X. We do the same thing here for like suffix sums going this way. And then we subtract out this part. Although we can count X separately, and so no, actually we don't. So let's just like assume now we know these values. So what do we end up counting? So assume these are, for example, here. Now here we count this whole value if we only consider the prefix sums or the suffix sums. Here we count this whole value. And this is the interval we want. So as it turns out, conveniently, that this is counted once, this is counted twice, and this is counted once. So the entire array is overcounted, like exactly the entire array. If we subtracted out the sum over the whole array, this would be 0 as we intend, this would be 1 as we intend, and this would be 0. So conveniently, we can just subtract out the entire array, and that gives us exactly the interval we want. And then from there, we can use the formulas to figure out the position we get. And this gives us the farthest to the right we end up, and the farthest to the left we end up, and then that just tells us like the farther of those two is the answer for this element. So to be able to do this, to have these be -1 and 1, we can simply process elements in increasing order, and then as we handle an element, we set it to 1. And that will have the values that are less than be set to 1. So for example here, in this code, we have 4 segment trees, one for max, one for like the highest values to the left and right, and the smallest values to the right, left and right. And then here initially every value is -1. So put basically says like set this value to this, and then it basically just updates the segment tree with the changes. So for example here, like if we update this value so we add 2 here, then if we're considering this tree where the prefix sums represent this, then the values that are affected by this change is exactly everything to the left. Because this includes this element, this includes this element, and this includes this element. So it's overall +2 on this interval. So we can do it with lazy propagation. And we can work out similar indexing for the rest. Then querying the min is querying the left and then the right, and then we subtract the total array, which can be like here. Also, you can like use the segment tree to figure out the total. Doesn't really matter either way. So now we try the left, and going to the left, initially we still set every value less than or equal to x to -1. So this would be less than or equal. This would be that. Wait. What? Wait. Yes. Yes. The value is less than or equal or -1. So this is actually to the right. So these comments are wrong, my mistake. So this should be to the right. To the right, we set less than or equal to -1. Because we want x to be the farthest to the right of all the values that are the same. So values that are the same will be considered less than it. And then we can just use this formula v/2. And then to the left, we do the same thing, except now we set equal values to 1, and then we query the maximum here, and then we use this formula. And then the answer is just the answer. Yeah. And also these values are initially 0, so if we get like nothing from either side, which doesn't make sense, but I guess that could happen, then it'll by default be 0. But it doesn't make sense that we get nothing from either side. Like we can always have at least 1, so that's fine. Do we have FSTs? Oh, my rank doesn't change. That's sad. So everyone above me, yeah, okay. So this, how much would I have got? How much would I have gotten had I gotten E? So points would be maybe like 1,100 or 1,000. So if I get 1,000, then it's 6,100. Okay, I would have done really bad. Yeah, no matter what, I would have done really bad. But this would have been a better really bad. Because right now is like within here, but like with a really bad penalty from the beginning. So if I had a better beginning, it would put me a lot farther. In fact, I would have a much better penalty on all of these. Maybe like 100 points each or something. I don't know. I don't know what to say about it. This was like a weird contest for me. I'm gonna submit E now. Let's see how this goes. Maybe I'll get a wrong answer. I hope I do. I really hope like that wasn't the only bug I had. Okay, it's gonna take a while. But yeah, so that's this contest, 34th. Basically around the same rank I get every time. Like I'm just consistently like in the 30s. I don't really get it. Running on test 8. Running on test, is it seriously gonna, okay, wrong answer on test 9, good. So that means that would be something else. So I guess I'll debug this and then like verify if my idea is right. And then, yeah. Hopefully it is. And then I'll just like go with it. I would assume that there's some bug here because there is a lot of room for bugs within this code. Actually, it's not that much, but there is some like a tricky indexing stuff that, I don't know, stuff could happen. Anyway, that's sort of it. I don't have more to say. Relatively standard contest, as to be expected. But, yeah. It's fine. It's a Div 2. It's not meant for me anyway. So, hopefully you all might have enjoyed it more than I did. Also, like, the fact that it was kind of early did not help either. But, whatever. I've done contests at 5 a.m. before. Or, like, 2 in a row. So this is fine. I don't have more to say. It's like a 3-hour video now. Okay, goodbye.